You don't have to final. You do have to do Alex.
Yes.
All right, find my derivative. The bracket at the end. I will give you a hint. You need to use the chain rule.
Review from here until the final.
Nope, I got some new lessons tonight.
Oh, okay.
We will be doing review the next week.
And then the following week?
Just the final, yeah. We only have 3 classes left. Yep, the 9th. We got the final early, which is great. All right, how do I do the chain rule? So it's always a question, what's the annoying part, right? The 1 plus x squared, that's the piece inside. So du, it's 2x. So then I've got 2/3 u to the 3 halves. Actually, d prime. So then we've got 1 plus x squared to the 1/2 times 2x. Correct? That makes sense? Huh? I said, does that make sense? All right, so now tonight's lesson is, what do we get to do? We get to go backwards. So what we're going to do tonight is known as the U substitution. Okay? It is the inverse of the chain rule. And it is probably the one thing you are going to use most often in integration. And it is also one of the first things you want to look for in integration. So if it's not a simple integration that you can just do, you want to look for your substitution, because all the methods that you're going to learn in chapter 7 in Calc 2 are designed to be all the cases you can't use substitution for. And they are a lot more complicated than use substitution. So we want to look at this way first So it is very similar to doing the chain rule. We just have to go backwards. So we're going to start with this 2x square root of 1 plus x squared. And just like when we were doing u substitution, or we were doing the chain rule, I said, what's the annoying part? The annoying part is the thing underneath the square root again. So we're going to make u the same thing. And then we du. So this is the one piece that changes. What's the derivative of that? That's 2x dx. So when you take the derivative of this side, that's how it's written. 2x dx. Okay. So now if I look over here, if I rewrite this a little bit, there is my 2x dx. So I can rewrite this problem as u to the 1/2 and then du. What's the integral of u to the 1/2? How do we do?
Where it's used the power of.
Yeah. So we add 1 to the exponent, bring it down, divide by it, right? Which in essence for a fraction flips it over. So we have 2/3 u to the 3/2 plus c. We can't leave it that way. We have to replace the u back with what it was. So 2/3 1 plus x squared to the 3/2 plus c. Exactly what I started with. Good, we're done. That's your substitution. Go. Just kidding. So here's the substitution rule. There are a couple rules. The u has to be differentiable. And the range has to be continuous with what was there. 99% of the problems that you're going to fall into or you're going to do will fall into this and will be fine. All right. Actually, I gotta do another one before I can have you guys do it. That's fine. All right, let's do this one. All right. So we can rewrite this as that. Whenever you have a root, you can always rewrite it as a power. So I have something inside of something, so I have to do kind of use substitution. Try that first. So what am I going to make my u? Two x plus 1. Okay? So du equals what? What's the derivative of 2x?
Yeah.
2. And the x is gone, so it's just 2 dx. Do I have a 2 over here that I can get rid of? So in this one, when we did it, notice that 2x dx was right there, right? So it easily canceled out, and that became du. Do I have a 2 over here to put with that dx? And no, that 2 does not count. So I don't have a 2. So I can only replace the dx. So how am I going to make this over here just dx? How am I going to get rid of the 2? Think back to your simple algebra problems. Divide by 2. So this becomes 1/2 du equals dx. So we're in essence treating the du and the dx's as a variable, as a part of the problem. Okay? They're not a separate piece. They actually do have something to be involved with the problem. So now I'm going to replace. So I have the integral of u to the 1/2. And then this becomes 1/2 du. So that becomes that. What can I do? Oh, with any constant, I have an integral. If it's just a constant times something. The rule that we saw was we can pull that 1/2 out. So I just have that. I can take that 1/2 and move it up in front of the integral. So what's the integral of u to the 1/2? Same thing we just did, plus c. So this becomes 1/3, and then I can replace the u back. So 2x plus 1 to the 3/2 plus c. All right, find your U and find your DU. What do you want to make you? So what's DU? Nope. We have the 2 times the, let's bring that down. It's okay. So negative 8 x dx. This is one of those things that is really easy to screw up again because we're doing differentiation, integration in the same problem. So certain things you have to make sure you go the right direction with your exponents, especially, and your sines and cosines will be another one. And we start working with those. That can be a little confusing when you're trying to go backwards and forwards at the same time. So, all right, what do I have over on the original problem that I can get rid of with what I have here? So I have an x and I have a dx, right? So in essence, I have that. So I got to move the 8 over to the other side. So I have negative 1/8 du equals x dx. So I could put the negative 1/8 right out in front. And I have u to the negative 1/2 power du. Because that's gone. And that is out in front. That only works if it's not a variable. As long as it's just a constant, you can just pull it out. All right. Now I find the integral of u to the negative 1/2. Yes. So we got negative 1/4. 1 minus 4x squared to the 1/2. Let's see. All right, I'm my integral of this one. Nope. You're close, but if it was just e to the x, yes. It would just be e to the x plus c. But there is a 5x there that has to have something changed. So think back, what's the annoying piece? The 5x. So make that your u and do the problem. And you'll see the extra piece you need. This is one of those problems that the more you do them, the more you do the problems that we've just been doing, the better you're going to get at recognizing the piece that's going to get pulled out. And you'll be able to do it basically without having to work it out. So when you have e to the x, we know it's just going to be e to the x. So you'd think, okay, e to the 5x. It's not too far off. If u is 5x, what's du? 5 dx. But I don't have a 5. So I have to change that to 1/5. Du equals dx. So this becomes 1/5 the integral of e to the u du. So it's 1/5 e to the u plus c, or 1/5 e to the 5x plus c. So in essence, now if I asked you to find me the integral of e to the 10x, we could just follow the pattern and go, okay, that's going to be that. You just go, okay, that's what it's going to give me that piece. Try this one. Anybody want to take a guess at what they think it is? What's you? So what's du? Do I have a 2x here? Yep. So as of right now, you cannot do this problem. I'm dying to see. Dying to see what AI gives me. Very good AI. This is actually a problem you'll never be able to do. Well, you won't be able to do through Calc 2. Might be able to do it in Calc 3 if they talk about it. There's actually, this one's actually is known as a non-elementary solution. So it doesn't have a simple answer. So, you know how you have imaginary numbers? This ends up giving an imaginary function. So there are situations, so not every situation you're going to be able to do the chain rule for. But it's easy to check that. Like you can look at it, this took maybe, 30 seconds to be able to do to actually see if it would work. That's why when you're getting to the higher and more complicated integration problems, we always say, check your substitution first. If you can do it, do that. It's going to make your life easier. If you can't, then move on to some other steps. So with that problem in mind, let's do this problem. Before we get to the trig problems, we'll do a more algebra problem. All right, try this one. What do you mean?
Like if you have UB like plus x squared and have another sort of variable or energy.
You could, but then you'd have multiple things trying to replace dx. What did you try? What did you try? Okay, what were you thinking of trying?
Right? U equals 1.
So then d is going to be what? Okay, the 2 is easy to deal with. I can pull the 2 over here, right? Let's see what we have left. Because we do have an x. We just have 5 of them, right? We have x to the 5th. So there's going to be something else going on. But let's see what we've got, and then we'll go from there. Because there's definitely something that we might be able to do. So I have an x dx here, right? So if I pull one of the x's out, so if I change this to, instead of x to the fifth, if I change this to x to the fourth times x dx, now I can replace that, right? So now I have that. So I was having a conversation with one of my high school kids today. She was doing the trig lessons, and you remember the trig, the pre-calc class when you were doing the problems where it was like tangent squared plus cosecant squared minus 1 equals sine squared x, like those problems, and you had to figure out the steps to break them down to it. And I was telling him, like, it's like a puzzle. Okay, it's a puzzle that you have to pull apart and put together. That's in essence what these are like. Okay, so what happens when we start to look at the higher ends of calculus is you have a ton of tools in your toolbox. You have all the algebra skills that you've learned, you have all the trig stuff that you learned. Like, you have these things to be able to manipulate problems. The key is which things are you going to use to manipulate it to make your life easier? So like in this one, I know I got to get rid of that square root of something inside. I've got to do some kind of u substitution for it. So I've got that piece done, but now I have x to the fourth still there, and I can't have two variables. I can only have one variable. Until you get to calc 3, and then you can have two variables. So how am I going to get rid of the x to the fourth? Look at the other stuff that I have in my problem. What else on this screen of the things that we did might be able to help me get rid of that x to the fourth? And put it in terms of u. What does u equal? Okay. What does x squared equal? U minus 1. You can manipulate this stuff over here. So when you're looking at this stuff that we have over here, this stuff over here, you can manipulate it. Those are equations. So we can change things in this. So that u equals 1 plus x squared, I can bring that over. So u minus 1 equals x squared. Not totally there yet, because I needed x to the fourth. But what can I do to this now to get x to the fourth? I can square it. So now my problem is, now it's all in terms of u. That's why I say these are like puzzles. You know where you need to get to. You need to look at the pieces that you have to see how to get to there. Okay. FOIL that out, do your algebra, because the way it's written right now, you can't solve this problem. You need to FOIL it out, spread it out. So we have a polynomial. Okay, so now we can find my integral. It's the integral of u to the 5/2. Yep. What was my u originally? 1 plus x squared. That's my final answer. So not all integrals are nice and small. And integrals can get very messy very quickly. What's the integral of sine x? Mm-hmm. It's the integral of cosine x. By the way. Oh, not dx. Why did I put dx there? Let's see. It's the integral of tangent x. Why? The derivative of tangent x is secant squared x.
Oh, I got that.
Look at your table from the other day, or from when we did 4.9 with the antiderivatives. This was my table. Tangent x isn't on there. Absolutely. So the reason it's not on there is because in essence we need to do substitution to do it. Now, you could make tangent x u, but then you'd have secant squared x, and we don't have that to get rid of. So, is there something else that I can do with tangent to possibly help me fix this problem? Okay. If I change this to sine x over cosine x. All right. What do you want to make your u? We only got two options, right? Either cosine x or sine x. So if we make it sine x, then my du is cosine x dx, right? But cosine's in the bottom, not in the top. So I would have to do a lot of math to be able to move things around. If we make it cosine x, then I have negative sine x dx, which is at the top. I just have to move this negative sign. So I have a negative sign out front. The sine x dx is gone. So I have 1 over u du. What's the integral of 1 over u? That's the ln. What should I change to make the negative ln of cosine of x to the ln of secant x? How is able to do that? What happens in ln's in logs when I have exponents? So remember, we can pull exponents out for a log, which also means I could put exponents back in. So that negative sign moved up here as a -1. Cosine of the negative first power is secant of x. It's 1 over cosine. You are typically going to see the derivative or the integral of tangent as that. So in most cases, you're not going to have to do the derivative of tangent. You have a rule for it. I mean, sorry, the integral of tangent. You have a rule. That's the rule. So that will become just like the rest of them. And that's a lot of the things with integration. Once you've done something, especially if it's a simple function, keep that rule so you don't have to keep doing it. There's enough other stuff that's going to make your life more complicated when you're doing integration. Simplify it as much as you can by taking things that are easy to use. All right, find me the integral of this one. We already did this. We already did this. But there's a 0 and a 4 there. So what kind of integral is this? Two types of integrals. One starts with a D. Yes. So this is a definite integral. So we have to plug in 4 and 0. Now, on this one, the next thing I'm going to show you is not going to make this problem that much easier. However, this process that I'm going to show you is going to make other problems a lot easier. Whenever you do a U substitution, so when we did this problem, actually, I'll just do it again. It's not a big deal. So I made the U the 2x plus 1. And then we had du is 2dx. And then we had the 1/2 du equals dx. These two numbers right here, I also can substitute. So I could do u to the 0. And u with the 4. So I can replace this whole problem. So 1/2 u to the 1/2 power du. And instead of putting the 0 and the 4 there, I put a 1 and a 9 there. This means I do not have to substitute back for x. My final answer I want is in a number. So by doing this, I don't have to make that final substitution back. I can just plug those numbers in. Like I said, this problem, probably not the doesn't save you a ton of time because it was a simple problem to do anyway. But let's say we went back to this crazy problem that we did up here. Not having to do that substitution back probably would have saved you a lot of work. Or a lot of trial and error, making sure you don't make a mistake when you're plugging them all back in. So we get the 1/2, 2/3 u to the 3/2. So we got 1/3 u to the 3/2. And we're doing that same thing. This time I'm going to do it from 1 to 9. So 1/3 9 to the 3/2 minus 1/3 1 to the 3/2. So it still comes out to be the same. Like I said, this one I don't think is going to save you a ton of work. There is a process in Calc 2 in Chapter 7 called trig substitution, where you're doing multiple steps and actually integrating back in a trig function for an angle. So you're going from x to trig functions, and you possibly have to do a u substitution. So if you do this, it saves you the trouble of having to go multiple steps back, which makes your life a lot easier. So remembering that you can actually do that is important and helpful. All right, one more problem, and then I will let you guys go.
The, can't remember what you call, but where the two and the one are, the greater value left is on top, right?
It doesn't have to. It typically does. But remember, if the greater value is on the bottom, we could flip them and just put the negative sign out front. That was one of those rules that one of the fundamental theorems of calculus where we could actually swap it and pull the value out. I see why you're asking. So these two values right here are opposite of the order you typically would have them in. You can swap them. This becomes, and that sign will swap. You don't have to. These two will come out to be the exact same answer. So I'm going to do it based on the original problem, but you can do it either way. So 2 minus 7 is -5 14ths equals 1/14. So like this one, I think it's a little easier to do the U values earlier than instead of doing them at the end. The only thing that would have happened if you had done the swap, the 1/2 and the 1/7 would have swapped. And it would have become a positive there, so you wouldn't have had the two negative signs at the end to multiply to get a positive. They would have been both positive, and you still would have got 1/14. That's typically why you swap them, is because you're going to get a negative value inside. But like I said, you don't have to. All right, we're done. And technically, you're done with Calculus 1. Next week, we'll do 2 days of review for the final, and then your final's December 9th.
When are the goals technically due?
Midnight on December 9th.
Okay, cool.
Because I'm going to start putting in grades after that point. So you have to the end of the day on the day of the final. Welcome. If you didn't get your test, come see me. I'll give you your test. What was your first name? So, name.
Get this video off. Oh, great.
I totally forgot to put up those. I will have them all up there tomorrow.
Happy Thanksgiving.
Happy Thanksgiving. That's not true.
Have a nice Thanksgiving.
You too.
I overheard you talking about the end of your plans, but didn't get started over your plans.
Oh, I host Thanksgiving.
Oh.
So everybody's my family all comes to my house.
Fine.
Yeah.